Dear Tim and Moby, are light waves, sound waves, and ocean waves all the same thing? From Danny. Well, all waves do the same basic thing, transfer energy from one place to another. But physicists divide waves into two basic kinds, mechanical and electromagnetic. Ocean waves, seismic waves, sound waves, and slinky waves are all mechanical waves because they need a medium to move through. Well, a medium is any kind of matter that's disturbed by energy. That energy disperses through the medium in the form of waves, which are basically chains of vibrating molecules. Water waves move energy through the medium of water molecules. Sound waves can transfer energy through a medium of air, liquid, or solid molecules. Seismic waves travel through the ground, usually after an earthquake. And slinky waves move through the medium of individual loops. Slinkies are really useful for visualizing how mechanical waves work. You can think of each ring as an individual molecule. When you shake one end of the toy, you can see how that kinetic energy moves from one slinky molecule to the next. Mechanical waves may appear to move matter forward with them, but that's not the case. Just like with the slinky's rings, a molecule disturbed by a wave will return to its original resting position after it's passed the energy onto its neighbors. Electromagnetic waves, like light and radio waves, don't need a medium to move through. They can travel through completely empty space. That's why light waves from the sun and stars are able to reach Earth. And why radio waves let us communicate with spacecraft. Well, mechanical and electromagnetic waves are different, but they can be measured in many of the same ways. This particular wave is called a transverse wave. It carries energy along the spring by making it move at right angles to the direction of the energy flow. Ocean waves and most electromagnetic waves move in a transverse pattern. The crest is the highest point of a transverse wave, and the trough is the lowest point. That distance between the midpoint of the wave and the crest is the amplitude. That's also a measure of how much energy the wave is carrying. More energy means a greater amplitude. The distance a wave travels in one cycle is one wavelength. That's measured by finding the distance between two crests or two troughs. Waves can be measured by their frequency too. The frequency is the number of waves that pass a given point in 1 second. It's measured in hertz, or waves per second. And frequency is related to wavelength. A wave with a short wavelength will have a high frequency, while a wave with a long wavelength will have a low frequency. Right, sound travels in compressional waves. Unlike transverse waves, compressional waves displace matter back and forth in the same direction as the energy of the wave. Vibrations created by anything from your vocal cords to a drum head to breaking glass will push air molecules together, forming a series of compressions that travel through the air. Those compressing air molecules hit your eardrum, making it vibrate and sending sound signals to your brain. Like I said, mechanical waves need something to travel through. That's why you won't hear sounds if you find yourself in outer space, unless of course if you bring your own air. Well, that's about enough on waves for now. Say goodnight, Moby. Ow!
And causes a sudden and powerful release of energy, so powerful that it breaks the Earth's crust. This fracturing emits shock waves through the ground and causes intense vibrations, or quakes. In fact, the world's most earthquake-prone regions are where the most geologically active plates meet. Earthquakes, or any seismic activity, are recorded by seismographs. When the ground shakes, seismographs oscillate, drawing a jagged line to reflect this movement. The more extreme the earthquake, the greater the height of the jagged line. These recorded motions are then used to measure the earthquake's strength, or magnitude.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next. run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesennuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall into Kamaishi City. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing. When 2 tectonic plates push together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11.